We've put triangles inside of the unit circle, but we've only done it in quadrant 1. We had this situation here. We have a 30, 60, 90 triangle twice in 2 different orientations, giving us, this 30-degree angle, right? This one's a 30-degree. This larger one is a 60-degree, and then this middle one here, that's that 45-degree angle. So we have those inside of there, and it's all in quadrant 1. And every single triangle we've drawn so far, talking about trigonometry, has been a certain way. It has two important characteristics. First of them being that that they are all right triangles. Okay, these trig ratios are only true for right triangles. The second being that these angles here are less than 90 degrees. They are acute. So what you could say, I guess, is that these trig ratios are only true when for angles of theta that are between 0 and 90 degrees. Right? Acute angles, that's what that means. Uh, but there's a clear issue here because we're talking about a circle. A circle doesn't just have a fourth of a circle. It also has these other quadrants, right? So, for example, right, what if I had this angle and I said, all right, so here's that angle now. It's talking about that angle theta. Well, how do I draw this triangle? Like, what are the trig ratios with respect to that angle theta? Would I like draw a line from here over to here and be like, okay, so which side is opposite, which side is adjacent, which side is the hypotenuse? Like, where is even the hypotenuse? Like, there isn't one. And so this is a big issue here. Like, how do I, for angles that are larger than 90 degrees, right, outside of this kind of domain, uh, how do we do trig? How do we apply the trig ratios? Now, the key to this is to stop thinking about trig ratios just as ratios, but as kind of as functions. Because what's interesting about a circle, and like it's an inherent property of a circle, is that as we go up, as we go around it, as we go like counterclockwise around it, you'll see that, like, for example, when we're right here, well, let's look at this. Let's look at this point right here, right? If I went over, actually, let's look at the 40, whatever. Let's look at this one here. As we go, as we're at this point right here, this XY, if we go directly across, right, into the next quadrant, that the coordinates here, that Y value is the exact same Y value, right? So this coordinate here is definitely root 3 over 2, the Y value. And then also, because circles are symmetric about the y-axis, this distance I went here and this distance I went here are the exact same, which means that if I went positive 1/2 from the y-axis to this original point, well, from the y-axis to this new point, right, that is just negative 1/2. It's just negative 1/2. And so this is also intuitive because we know stuff about the quadrants of a coordinate plane in quadrant 1, right? This is quadrant 1, that the signs of x coordinates are positive and signs of y coordinates are positive. In quadrant 2, quadrant 2, right? The signs are negative x values and positive y values. In quadrant 3, these signs are negative x's and negative y's. And in quadrant 4, the values are uh, positive x values and negative y values. And so you could see that we could kind of draw these angles out over here. And so if I wanted to know, right, if we define sine of theta, so for example, this one, like, because we drew that point right there, if we define and we had now this angle theta, then I would be able to say, well, the sine of theta is the y value, so it's that. Right, the sine of that angle theta would be root 3 over 2. The cosine is the x value. Okay, so I'd be looking at this. And what we get here, what we can see, is that it would be just like if I, instead of having that larger obtuse angle I drew, what if I kind of substituted it for what would be the complement of that angle? So what about this acute angle instead? What if we called that's like our like stand-in for theta, kind of. And this is what we call reference angles. The other thing that's interesting here, if you think about sine, if you think about the y values, if we started at 0, right, the sine of 0 degrees, let's put a 45-degree angle right there. we'll put a 90 degrees right there. That's 90 is vertical. And then we put 135 degrees, that's another 45, and then 180 degrees, right? If we kind of graphed, if we went this way in theta, and we said we can have a maximum value of 1 and a minimum value of -1, for sine, if we're looking at sine of 0 degrees, right, the y value is 0, so we'd have a 0 right there. If we look at the sine of 45 degrees, it's root 2 over 2, which isn't 1, but it's like more than 1/2. Okay, and then if we look at sine of 90 degrees, that's just 1, right? So we'd have a point right there, 1. And then if we go around, you notice now it's symmetrical. It's going back down, so we'd have a point here, just straight across from where our other point was. And then 180, if we put this coordinate here, right, it's -1, 0. So the y value there is 0. And so this graph, like the sine graph, kind of does this thing. And this is actually this graph of a sine function. And if we kept going, it would do this, and it does this interesting periodic pattern that we'll learn more about in the future. So applying that thinking here to 30 degrees, our original angle is 30 degrees. That means that if we drew this line straight across, right, this angle here would be 150 degrees. It has a 30-degree reference angle in quadrant 2. 150 degrees is a 30-degree reference angle. 30 degrees means off the horizontal. So all these reference angles, are from the horizontal, not from the vertical. So this 30-degree angle here, notice the coordinates root 3 over 2, 1/2, and root 3 over 2, 1/2. They're the same. Root 3 over 2, 1/2, root 3 over 2, 1/2. All we need to do is adjust the signs of the coordinates, right, to match up with the coordinate, or for the quadrant of the coordinate plane that we're in. So this angle here, this larger angle, that's 180 plus 30, so that'd be at 210 degrees, right? If we did the entire the 30-degree reference angle in quadrant 4, that would be 330 degrees. And so all of these angles, basically we have the same coordinates, same values for sine and cosine. For all of those angles, all we have to do is adjust the sign depending on what quadrant we're talking about. Similarly here for the 60-degree angles, right? This first angle is 60 degrees. If we go 60 degree, if we have a 60-degree reference angle in quadrant 2, that angle is 120 degrees. If we had a 60-degree reference angle in quadrant 3, that would be 240 degrees. And if we had a 60-degree reference angle in quadrant 4, that would be 300 degrees. Okay, so all of those angles, all of those 60-degree reference angles, they are 60 degrees off of the horizontal in each quadrant. They all have the same coordinates, which are 1/2 and root 3 over 2, except we change the sign depending, again, on which quadrant it is. So, right, quadrant 4 has a positive x, a negative y, positive x, negative y. Quadrant 3 has both negative. Okay. And then finally, 45-degree reference angles are the same thing, right? We have 45-degree angles in each quadrant, 45-degree reference angles, so 45 degrees there. If we go 45 degrees in the next quadrant, sorry, I messed that up. 45 degrees in the next quadrant would give me this 135 degrees. If we go 45 degrees in quadrant 3, that'd be 225 degrees. And if we go 45 degrees in quadrant 4, that is our 315 degrees. And they all have the same coordinates, root 2 over 2, root 2 over 2, and all we have to do is change the signs depending on what quadrant they're in, what quadrant we're in. So where that leaves us here, and this is a pretty intimidating looking picture, but this is basically the entire unit circle. There's something pretty important, couple of little things we haven't talked about yet. But for the most part, that's the idea behind the unit circle. That these values for sine and cosine, they just keep repeating themselves over and over and over again. And in that way, they are sine, cosine, and tangent actually are all cyclical functions. They are periodic, meaning that the values will continue to repeat, and the interval over which they repeat is constant. And we'll talk more about how to look at trigonometric ratios as functions a little bit later, there's two different ways to think of how the unit circle works. It's either this way, where we kind of have an intuitive knowledge of the sign changes in each quadrant, or as functions. And so the power of this now is that if I wanted to know what's the sine of 300 degrees, I would recognize that 300 degrees as being a 60-degree reference angle in quadrant 4, and I know that 60-degree reference angles have coordinates of 1/2 comma root 3 over 2, and because I'm in quadrant 4 where the y value is negative, I just put a negative in front of the y value. So that's the coordinate point, right? And if I'm asked for sine of 300 degrees, I'm talking about the y value. So the answer to this is just negative root 3 over 2. The cosine of 225 degrees, I recognize that as a 45-degree reference angle in quadrant 3, and it's the x value. So this would be just negative root 2 over 2. If I wanted the tangent of 240 degrees, I recognize that as a 60-degree reference angle in quadrant 3. Okay, the 60-degree reference angle here in quadrant 3. 60-degree angles have a tangent of root 3, right? We can say that it would be, so 60-degree coordinates are 1/2 comma root 3 over 2. This is y, this is x. Tangent is equal to y. Tangent of theta is equal to y over x. So that would be root 3 over 2 divided by 1/2, which is the same thing as the square root of 3. So tangent of 240 degrees is the square root of 3. If both of these were negative, I'd still have a positive root 3. And so we can find the values for sine, cosine, and tangent for any of these angles now. There's a whole bunch of them here.